In this video, we look at some applications of radian measure. We'll start with the area of a sector of a circle. So a sector of a circle is like a pie piece where the point is at the center of the circle, and the two sides here are both radii. We're going to start by looking at the fraction of the circle represented by that sector. We could calculate this two different ways. If we knew the area of the sector, we can write that over the area of the entire circle. And that's going to tell us the fraction of the circle that the sector represents. We could do this another way. We could look at angles. So we're going to call this central angle of the sector theta. And if we look at the angle that would be, if we went all the way around the circle, then that's one complete revolution, or 2 pi radians. Okay? So either way we calculate the fraction of the circle present, it's the same fraction of the circle, so these two ratios are equal. Okay? Well, we know a little bit more than what I've written. The area of this sector is what we'd like to find. Let's just call that A. The area of the entire circle. We can calculate that using an old formula from geometry. It's pi times the radius squared. Our radius is r. The central angle theta, and then 2 pi. Now, one thing I should point out is it's pretty important theta is in radians, since I've used 2 pi radians to represent the entire circle, or all the way around it. Okay, so let's solve for A, the area of the sector. Multiply both sides by pi r squared. We can divide out those pi's and then sort of rearrange what's left. The area of the sector is 1/2 the radius squared times theta, with theta in radians. Now let's practice using this formula. In this example, we're asked to find the area of a sector of a circle where the central angle is 40 degrees and the radius is 5 centimeters. So we've just found this great formula. The area is 1/2 r squared theta, but theta needs to be in radians. So that's our first problem. Okay? So whenever we're using a formula, we should always write it down before we begin, and then we can substitute in there. But as we've discussed, this needs to be in radians. So we're going to take our 40 degrees and to the side here, convert that to radians. How do we convert? Pi radians is 180 degrees. So we're going to multiply this by pi over 180 degrees. And for now, we're just going to reduce that to lowest terms and keep it as an exact value, so I can go a little bit further. That's really 2 pi over 9. Okay? Now we're ready to substitute. The area is 1/2 the radius, which is 5 squared, times 2 pi over 9. Now I should stop here because my instructions didn't really tell me how to leave my answer. So we're going to start by giving an exact answer that's left in terms of pi, and then we'll approximate it if we need to later. Okay? All right, so what can we do? Well, 1/2 times 2 is 1. So I can write this as 25 pi over 9. Okay? What kind of units would the area of the sector have? The radius is given in centimeters, so area should be in square centimeters. Okay? This is an exact version of our answer. Sometimes you're asked to approximate your answer to 1 or 2 decimal places. At that point, you would take your calculator out and multiply and divide on your calculator to get an approximation. Let's do that real quick. So this is approximately 8.73. So we're going to use 2 decimal places here. Centimeters squared. And the number of decimal places will always be told to you in your homework or in any problem that you're working. Here's a second example of the area of a sector of a circle. Find the radius of a sector of a circle given the central angle is 3/5 radians and the area of the sector is 600 square feet. Round our answer to 1 decimal place. Okay, so we know we can use that formula. Area is 1/2 r squared theta for a sector of a circle. Theta needs to be in radians, so let's check that first. Great, this time we have our angle given in radians. But what's the difference in this problem? I'm not looking for the area. I already know that's 600 square feet. I know the central angle, but I need to find the radius. So the algebra in solving this one's a little bit more involved. Okay, so let's start by substituting what we know. The area of the sector is 600. The radius is what I'd like to try to find, and theta is 3/5 radians. Okay, I'm going to simplify the right-hand side by multiplying those fractions. That's 3/10 times r squared. And I need to get that r squared by itself. So let's multiply both sides by the reciprocal of 3/10. That would be 10/3. So we have 10/3 times 600 equals 10/3 times 3/10 is 1. So this is just r squared. Okay. 10 times 600 is 6,000. Divide that by 3, so we have 2,000 equals r squared. Now that's not a perfect square, so I'm going to grab my calculator so we can approximate it. R is going to be the square root of 2,000. Certainly going to be a positive number because it's the radius of our circle. The square root of 2,000 is about 44.7 rounded to 1 decimal place. What would the units be for our radius? Well, the area of the sector was in square feet, so our radius should be in feet. Next, we're going to look at arc length. This is the length of an arc or a portion of a circle. Okay, so I've drawn a circle with radius r. This is the center point. I have central angle theta again, and the arc is labeled S, and it's this portion of the circle intercepted by the central angle. I'd like to be able to calculate the length of that arc, knowing just the central angle and the radius. I'd like to look again at fraction of the circle represented by, in this case, the arc. Okay. So we're going to do the arc length over the circumference or distance around the entire circle. And then we're going to look again at the angles. So the central angle for this arc is theta. And an angle that starts here and goes all the way around the circle is 2 pi radians. So again, we're going to have that stipulation that theta has to be in radians. Okay. Now we've written the fraction of the circle present 2 ways, but they're the same fraction of the same circle, so they have to be equal. Okay. Arc length, we're going to use the letter S. Circumference of a circle, do you remember that formula? 2 pi times the radius of the circle. Okay, let's solve for S. Multiply both sides by 2 pi r. Notice that the 2 pi's divide out for us, and we're left with a very simple formula. S equals r theta, theta in radians. Let's practice using our arc length formula. We'd like to find the exact length of an arc of a circle with radius 10 feet that's intercepted by a central angle 330 degrees. So we have this nice formula, S equals r theta, but theta has to be in radians. We're given the central angle 330 degrees, so before we do anything else, we need to go ahead and change this to radians. There are pi radians in 180 degrees, so we're going to multiply by pi over 180. So this one just is 33 pi over 18. Oh wait, I can go further. Those both have a common factor of 3. So this is really 11 pi over 6. Okay? Now we substitute. The radius is 10 feet. Theta is 11 pi over 6. Think of this as 10 over 1 and reduce your fractions. So I'm going to just go ahead and multiply. 10 times 11 is 110 pi over 6, and then reduce that. What kind of units would arc length have? Well, it's just a length. So whatever the length unit is used for the radius, we'll use for our arc length. So 10 feet. We wanted an exact value, so we want to leave it in terms of pi and an improper fraction. Here's another example that uses our arc length formula. Find the central angle of a circle with radius 30 inches that intercepts an arc of length 10 inches. Okay, so we can use our arc length formula, S equals r theta. And in this case, we're looking for the central angle. Okay, so that's what we don't know. Our radius is 30 inches, and the arc length is 10 inches. So an arc of length 10 inches, this is the S in our formula. R is 30. Okay. If we divide both sides by 30, we'll have theta by itself already. So theta is 10 over 30, or 1/3. 1/3 what? What are the units for our angle theta? Right. So theta, in order to use this formula, has to be in radians. So when we solve this, we're finding our angle theta in radians. If a particular problem asks you for that answer in degrees, then you know how to convert from radians to degrees, and you can do that at that time. So you need to learn both of these formulas for area of a sector and for arc length. Don't forget that your angle theta has to be in radians each time that you use them. And then practice these examples until you're comfortable with these skills.